It is April 2026, and humanity is standing on the threshold of a major milestone. Artemis II is in its final preparations to launch a crew into lunar orbit. Only 12 humans have ever walked on the moon, a record that began in 1969 when Neil Armstrong took that first tentative step. They achieved that using the Saturn V rocket, a towering analog machine running on an Apollo guidance computer with roughly 64 kilobytes of memory. That is less storage than a single plaintext email. If engineers successfully landed humans on another celestial body half a century ago using mere kilobytes of data, the current timeline seems counterintuitive. Returning today is proving to be more complex, slower, and more demanding than the original effort. The Apollo missions were designed for a specific objective: get there, collect rock samples, and return. Artemis is built around a different requirement. We are no longer designing vehicles for a brief visit. We are engineering the infrastructure to stay. This formula is the Tsiolkovsky rocket equation, and it proves that the physics of leaving Earth remain identical to the 1960s. To break orbit, a rocket's thrust must overcome the immense weight of the ship and the pull of gravity. What has changed is the destination. Apollo astronauts landed near the lunar equator, regions that are relatively flat and bathed in sunlight. Artemis is targeting the lunar South Pole. Engineers selected this region because those deep, permanently shadowed craters contain verified reserves of frozen water. Accessing that ice requires operating in a hostile environment, navigating jagged terrain with virtually zero natural light. Beyond the terrain, the environmental hazards are severe. Without the protection of Earth's magnetic field, crews face prolonged exposure to heavy cosmic radiation. The ground itself is covered in regolith, an ultra-fine, abrasive dust that degrades machinery and poses health risks to the crew. The lightweight lunar modules from 1969 were not designed for these conditions, and operating at the South Pole requires a heavy-duty engineering architecture, capable of withstanding months of exposure rather than days. Delivering that architecture starts with a modern heavy-lift transport system. Instead of the Saturn V5, NASA relies on the Space Launch System, or SLS, to push massive payloads into orbit. For transit, the crew relies on the Orion capsule, while the heavy surface equipment and habitats required for survival will be delivered by SpaceX's Starship. Once they reach lunar orbit, the landing protocol changes. Apollo pilots manually steered their landers to avoid boulders. Touching down safely in pitch-black craters now relies on AI-assisted sensors and autonomous navigation software calculating the trajectory in real time. When astronauts finally step outside, they cannot rely on the restrictive suits of the 1960s. Constructing a lunar base demands heavy, sustained physical labor. They will wear the AX-EMU suit, which provides a massive increase in joint mobility and incorporates structural reinforcements to block out the sharp, abrasive regolith. Long-term occupation depends on a process called in situ resource utilization, or ISRU, the capability to mine and process the ancient ice deposits hidden in those South Pole craters. This flowchart demonstrates the necessity of ISRU. Extracted lunar ice is chemically split to provide 3 essential outputs: drinking water for the crew, breathable oxygen for the habitats, and liquid propellant for the rockets. Hauling millions of gallons of water and rocket fuel out of Earth's gravity well is financially impossible. By manufacturing these resources locally, a permanent human presence in space becomes logistically viable. This wave of deep space engineering is also drawing a wider crowd. The 1960s space race was strictly a contest between 2 superpowers, but the lunar surface of 2026 is a multipolar arena. Much of this effort is cooperative. The European Space Agency is deeply integrated into the Artemis program, contributing directly to the construction of the new orbital lunar gateway station. There is also intense competition. China has committed to a timeline for its own lunar base, and India has already successfully soft-landed its Chandrayaan-3 probe at the lunar South Pole. This international race for the lunar South Pole establishes a high-stakes strategic laboratory. Extracting ice, maintaining closed-loop life support systems, and operating machinery in a high-radiation vacuum are mandatory survival skills. The moon is the required dress rehearsal to verify the technologies we need to eventually land humans on Mars. Yet, The engineering effort and financial capital required to survive off-world are staggering. We are pouring immense resources into deep space infrastructure, while simultaneously facing urgent environmental and economic crises back on Earth. As we build the physical foundation to expand beyond our home planet, we have to look closely at the cost. We must decide if the resources required to settle the stars are a price we are willing to pay.